And I will show you this as we go through this lecture. The lecture will last approximately an hour and a half, and it's on spectral bands and their applications. And those spectral bands I'll deal with are mainly the visible near-infrared and infrared bands. So you can see those are what I will focus on. And at the very end, there's a short section on microwave and active sensors. If you want more information on microwave, go to the virtual laboratory. But we will see there is a very interesting microwave product that you should make sure your CMA colleagues work with on a routine basis. So we want to, some of this we've already done, know the difference between visible, near-infrared, and infrared channels, or understanding the difference in what we see, the basic principles behind channel selection, what influences it, information that can be obtained from the various channels. We want to understand how to interpret the information and the difference between multispectral data and hyperspectral data, because those are terms that we see a lot. Dr. Menzel covered this yesterday. This is the emitted energy from the sun and the earth, the Planck function. This is in terms of wavelength. And this very interesting overlap portion at 3.9 to 4 microns is of particular interest because it has both emitted and reflected solar radiation. Or emitted Earth radiation and reflected solar radiation. And actually, if you get fires that are hot enough, most fires actually have their maximum emission down in this range around 1.6 to 2 microns. This is just a diagram, a simple diagram of what Dr. Menzel talked about yesterday with incoming solar radiation. About half of it gets to the Earth's surface as an absorbed. Then you have some that is absorbed by the atmosphere, mainly ozone, water vapor, dust, main absorbing constituents. Some is backscattered by the air. That's the scattering that gives you the blueness of the sky, scattered back to space, so mostly short wavelengths up here. We get reflection by clouds and also reflection by the surface. And that accounts, if you add all the numbers up, you'll come up with a balance of about 100 in, and the rest is absorbed and this much out. Now, of that energy coming in, that which is absorbed by the surface, so this 51 equals this 51 that's emitted by the surface, part of it goes directly out towards space, being absorbed, of course, by water vapor, CO2, methane, some of the very active gases, mostly CO2 and water vapor. Some comes as a sensible heat flux, and others appear as latent heat flux, and you get emission by the water vapor and CO2 Dr. Menzel talked about, as well as emission from clouds that comes straight back out to space. I brought this forth in Lecture A, or the very first lecture that I presented here, and that today we're digital and multispectral. And what you really need to very clearly understand is every element that you look at, every spatial element has a continuous spectrum. And we can utilize that spectrum to analyze the Earth surface and the atmosphere. Now this is an example of that from this Abris instrument that was introduced yesterday, and I'll go into it a little bit more. But a continuous spectrum, now part of that is absorbed immediately, part of it goes on out to space, part of it is reflected. One advantage of being digital, of course, is to be able to go into individual images and analyze them better. And one way we do that is in the 10.7 micron infrared window channel area, where we can take the digital values and we can convert them to temperature, and then assign each temperature a different color. And when we do that, it makes it easier to understand something, for example, like a thunderstorm top. This is a picture of a thunderstorm. On the bottom, we have an enhanced visible image. You can also enhance the visible imagery by looking in certain brightness areas to get a better definition of features. Here we've enhanced to show the thunderstorm top better, and we can see the overshooting turrets. Mainly you can tell they're overshooting turrets because downwind you see they cast a distinct shadow. So you know the sun has to be over here, coming in, hitting this side is bright, and the shadows cast downstream. So what we can do then is go and compare our infrared data at high resolution, which we have day and night continuously, by enhancing the cloud tops, and we see where we're blue and colder, we have the colder overshooting tops that correspond very well to the overshooting top regions that we see throughout one image or another image. So the ability to enhance infrared data so you can see the detail in it is very important, and that's one thing that happens because you're digital. So you can handle each channel individually and squeeze information out of each channel by itself, or you can do them in combination and get other very important information. When we look at investigating with multispectral combinations, we actually went over this quite a bit yesterday. This is wavelength in nanometers, or this would be 0.3 microns about to 2.5 microns. Okay, so it's microns or nanometers. Here's where your eye works in this region, where we get a lot of reflection of solar radiation from this area. And we realize that grass and vegetation is very poorly reflective until we get out to about 0.7 microns where it becomes highly reflective. So we can use the difference in that and find out something about grass and vegetation. So we have channels that are historically around 0.65 microns and around 0.85 microns. Therefore, we'd have one channel that's very reflective for grass, one channel that's poorly reflective for grass. And we can go in and difference those two channels and then divide by the sum of those two channels and get what's called a normalized derived vegetation index, or Ndvi, that you hear about quite often. And this is just an example of Ndvi, where we turn the areas that are the brightest, biggest difference between 0.86 and 0.5 divided by their sum. We turn those bright green in areas that are almost the same between here and here, so you get a zero difference because there is no grass or soil. Then you get a difference like this, so you get much less of a difference. Now the question on channel selection came up yesterday is why don't we just go out and use a channel like 1.6 difference from 0.5 to do derived vegetation index, because we still have a higher value here for grass than we do at 0.5. But if you look, the value for grass and soil are about the same, so it really wouldn't be a very good channel to use that difference for normalized derived vegetation index. If we went out further into this region and tried to use information out here at this 2.1 micron channel, the soil would be brighter than the grass. So we could, I guess, do a derived soil vegetation index. But one of the things that happens with the reflection off of water is basically non-reflective past about 0.7 microns all the way out to a little past 2, but then it becomes reflective again. So those type considerations need to be taken into account when you derive the channels or choose your channels. So what you can do with clouds, variability in clouds, when you have a sun-synchronous polar orbit that you're coming over basically at the same time every day but with slightly different viewing angles depending on where the orbital track is, you can pick the Ndvi areas on a day-by-day basis and get rid of the clouds so that you'll come up with some fairly well cloud-cleared land areas after 10 days. For example, here's a true color image from MODIS. So here, and here's the Ndvi from that MODIS. So you can see that there are clouds in the area. These blue areas in the right-hand portion are clouds, and also there's ocean down here, which is blue. But the green areas up near the top of these strips is the Ndvi showing vegetation. So you can look at your, quote, true color image versus your Ndvi image and see that actually you can see vegetation better with the normalized derived vegetation index. And on the right are 3 time periods over 10 days each with Ndvi, and you can actually see how vegetation is changing in time, where its condition is growing worse, either it's less green or it's growing better, more green. And over this period, there was mostly vegetation not as good during this time of the year. It was decreasing its greenness. So products like that can be very valuable. There's also differences in absorption and scattering from dust, and you can do similar products to find dust or volcanic ash with the 12 micron and the 11 micron channel. And when we look at something like that, this is a movie of the dust storm over Africa, so it's a huge area, and the large pink region that's moving is dust, and a lot of that information comes from the difference between the 12 and 11 micron channel. Also, the 8.6 micron channel enters into this, and I'll show you why in a minute that becomes important when you're looking at things like dust or sand. We'll see this particular image that's in animation now. Again, but you can see while dust appears pink, it makes some of your cirrus clouds look a little different than you might normally look at them. Now let's look into more detail right now, though, at the visible and near-infrared portions of the spectrum and try to get an idea of some of their unique characteristics. Now, we talked about channels yesterday, again in this 0.4 to 2.5 micron range. Again, the 1600 nanometers would be 1.6 microns. If you look in the very short wavelength area, there's a lot of atmospheric scattering of the blue. That's why we see the blue sky that we do. And as you go on into longer wavelengths, you'll notice we begin to get absorbing features, molecular oxygen, water vapor. This O2 region, right around 765, is called the oxygen A band. It was one that you were considering, I think. There's water vapor absorption regions. You also have CO2 absorption. Now, one of the things that we'll look at on this in a minute is we're going to go through this step function movie again and see different features appear at different wavelengths. So when we're beginning the movie, there's a lot of scattering, and that's just molecular scattering. We're not seeing down to the ground at these very short wavelengths. We do pick out part of the cloud. I'm going to start and stop this movie and try to concentrate on certain ranges. So we're going to start the movie, and I'll stop it right here. Now we're at about 500 nanometers or 0.5 microns, and we're beginning to see down toward the surface. We're picking up a lot of dust, and we have a cloud top that shows up very nicely. Here you can see the structure in the cloud, and then some thicker dust. Now this is about 10 meter data taken from an instrument called AVERS, but it's very good to illustrate points. Now as we go to longer and longer wavelengths, of course the scattering by the dust and the aerosols gets less and less, and they appear to go away. So here we are at 0.5. I'm going to stop it again right out here at 0.7 microns, a little bit beyond 0.7. You can see the dust is going away, but also if you're watching the ground over here on the bottom part of the picture, you'll notice that it turns brighter. And that brightening of the ground that we see, again, is because vegetation is more reflective as we go out past about 0.75 microns. So here's the cloud. Now we're going to go out further. I want you to notice also how the different parts of the ground change their brightness depending on wavelength. It's very interesting to watch. So we'll go out a little further. We're going into our first water vapor absorption band, so we begin to absorb a lot of the reflection, and we don't see down to the surface as well. We're still losing our smoke. We go through that band, and now we're at another area here where we're about to enter into another absorption region. You'll notice the smoke is starting to disappear very nicely. We've had changes in the land brightness. You can see part of a river through here because we're out in the region where water turns basically black. You just don't get reflection from water. So that and the lake up here show up very well. We're beginning to see the shadow of the cloud. Now we're going to go through the water vapor absorption band. We're getting a lot of reflection off the cloud, but notice as we go into water vapor absorption bands, we'll go out of it into this very deep band here at about 1.5 microns. And you don't see the surface, you only see the top of the cloud. But one thing that you are seeing right in here is a bright region just to the left side of the cloud. And that's actually emission from the fire. The fire's temperature is around 900 degrees K. You can use your Wien displacement law and find out where 900 degree K is. Somebody can tell me that at the end of this, where your maximum wavelength of emission is going to be for a 900 degree K fire. We have this gentleman right here working on it right now. But you can see now we've cut out a lot of the water vapor. We see more detail in the cloud. We come back out of the absorption band and look at the changes in land. So we see a lot of changes in land characteristics, and this is because differences in reflection and emissivity of the land surface properties. Now we're going to go back into another deep absorption band here in just a minute. Again, we're following this red line. So we go in and down into that absorption region, and it is so deep we just see the top of the cloud. We barely see any of the fire emission, but we have detailed structure in the top of this what's called a pyrocumulus cloud. Now we're coming back out of it. We hit some other minor absorption regions, and I'll stop it right here about a little past 2 microns. You're going to notice the lake and the river are not showing up near as distinctly as we moved along the wavelengths. Again, we started to reflect more off of them, but our land characteristics are changing dramatically, and the fire is very, very bright now. And this is due to emission at this wavelength, and now we're going to go back into a absorption region out at the very end. So being able to use hyperspectral data to look at a scene is absolutely incredible, because you can go in and at each pixel, actually, you'll see that there is a different characteristic spectra as you move across the image. So you can very clearly see the difference between cloud, fires, grass. You'll notice the grass, the abrupt change in brightness when we went past 0.7 microns. Here water is, the blue line. Notice that it becomes very poorly reflective until we get out to about 1.9 microns, then its reflection picks up again. So we can use this to find small smoke particles from large smoke particles, because the small smoke will apparently disappear at the shorter wavelengths before the larger particles do. So there is a wealth of information that we can use if we have hyperspectral data. If we don't have hyperspectral data, what we do then is go and choose our multi-channel combinations from this. Now this is a very interesting picture. If you look here, this is a true color. This is what you would see something like if you looked out of an airplane over this region with your red, blue, and green channels enhanced in here. And we see a runway for an airplane right here, and we see all of this different colors in the whatever this is out here. And if I ask you, show me where the islands are. Show me where there is just island, because this is a scene in water. How could you do it? Well, one way certainly to do it would just be to choose 3 channels that were where water was non-reflective. And that's what I've done over here on the right, the non-reflective water bands. So you don't see the shadows of these clouds that are in the upper right. You can see the runways very well, but some of the islands that are on the left-hand side of this image you may not have picked out at all. So again, depending on your application and what you're doing, being very crafty when you select the spectral bands you look at and combine, give you different information. So we have one set here that's showing us ocean color, some color in the ocean. We eliminate the ocean, we get very accurate registration in gridding, for example. These are the bands, we looked at them yesterday, that are chosen on the various satellites to do their work. You'll notice that on ABHRR, which has been one of the workhorse satellites over a number of years, that while we had the 0.6 micron band here, our 0.85 micron band actually sits where there's water vapor absorption. Now this band was put on mainly for gridding and registration. We actually want, and ice, melting ice, because if you get ice or snow that is not melted, that band will be bright, but when you put water over the top of it, you remember water is non-reflective out there, so when it comes water over the top, you can tell the snow is melting. So that's one reason this band at 0.86 is here, but it has this water vapor absorption. This has been a workhorse band for Ndvi for years. And what should that tell you immediately about Ndvi and tropical regions? You have water vapor absorption going on in that band and what is reflected out of it, so it will be less green than it should be. So part of the variability you would see in there could be due to water vapor absorption. Now, why the various bands and the width of the bands? It's complicated. I talked about it before, but it comes back to the spectral resolution, the energy, and the signal to noise that you need to get to diagnose the scene. So you may have to make a compromise by making a band too wide. But if you do, you should understand what the consequences will be. Now this is an image from MODIS that I want to show you. It goes a number of bands. I don't need to read their wavelength to you. You can see it. I'll just point out this is 0.4, 0.9. This is 1.2, 1.63, 2.1. And it's a daytime view of water clouds and ice clouds. And you can see that when we're in our conventional bands that we look with, that everything is bright. Ice is fairly bright and reflective. Water clouds are fairly bright and reflective. But as we begin to move out to the longer wavelengths, here's 1.2 microns. The ice cloud is still reflective, but when we get out to 1.6 microns, we begin to see the effect of the larger particles on the reflection back into the satellite telescope, and ice begins to appear as dark, much darker. And when we're out at 2.11, you'll notice the ice clouds are very dark, and even some of the larger particle water clouds are dark. So you can imagine how you might use a channel at 2.1, 1.63, 0.96, 0.55, and start to try to say something about particle size and particle type in a cloud. Okay, because you do have different brightnesses due to whether it's ice or water. Large water droplets are less reflective than small water droplets, and this begins to show up as you get out to longer wavelengths. Now you can take information like this and do multi-channel combinations, and that's what I've done in this that is not visibly very appealing. Look at a thunderstorm, but you can see that by putting these channels together in a red, blue, green combination, and you can do your own and try out your own and see which one you like best. But the clouds can appear, where they're ice clouds is this pinkish color, and where it's water clouds is this white color. So rather than giving someone 3 different pictures, you can give them one picture if you tell them what it is they're looking at. Now, what I want to do is look at reflection from the 1.38 MODIS band. And 1.38 is in this deep water vapor window. And what I've displayed here is the energy reflected back to the satellite. So you're seeing a relationship between energy Where there's a lot of energy, it's white. Where there's very little energy, it's black. And now we're going to go out to a band at 1.38 that's very close to this, and I'll ask you what you think the thunderstorm type should look like. And when you look, you actually see, oh yeah, because of the deep water vapor absorption, I'm getting no reflection down in this area. All my reflection has to come from that higher thunderstorm top. And that's why it appears as white here. But this is definitely ice cloud because I'm not getting down into my surface area. So we have lots of ways using multi-channel data to distinguish ice, water, particle size, and so forth. This is just another example. Here we are at 0.64. Here we are at 1.64 microns. You can kind of see some shadows or dark areas. If we look at 1.38 microns, the Cirrus stands out very well. So this is an important channel for you in the FY4 satellite series. Unambiguous Cirrus detection. If we look at ocean color, as illustrated by sea whiffs, we look down in these very short wavelength regions right here, and we try to look around, I can't remember the exact bands, but these are the bands that we look at, and one of them is very active in the chlorophyll area, chlorophyll A, and we try to say something about our ocean color. And this is an ocean color product from MODIS showing the abundance of chlorophyll across the ocean. And you can derive things like this from your polar system if you have very, very high quality channels down in this short wavelength area. And again, you see the higher chlorophyll abundance near coastlines in here. There's some in this upwelling area where you have that return cold current that goes with a La Nina. You remember how the currents in the ocean run maybe. You can see the abundance of chlorophyll up here, but if you look across this region, that's where the ocean desert is. Just like there are deserts over the earth, there are deserts over the ocean. And you can get the amount of chlorophyll in milligrams per cubic meter with this. And this is all near surface reflection. You can also go in and look at aerosol optical thickness. Now, how would you do that? Well, you take short wavelength versus longer reflective wavelength channel. You can separate out your contribution from small particles and the contribution from large particles. You remember the movie where we showed the small particle smoke and large particle. So we can see the difference. Again, these are products that you can do routinely. This is a movie of dust. It's from Meteosat. It uses 0.6, 0.8, and 1.6 micron channels. The 1.6 micron channel, again, that's why these clouds are blue. They're ice clouds, non-reflective, so you've got a color combination that gives you that. The dust front shows up very well. You can also see evidence of greenness. That greenness is going to be because of reflection at 0.8 and at 1.6 microns versus not at 0.6. The dust front shows up very well, as do different characteristics of the land in the desert area. So we know there are differences in emissivity and reflection that are going to occur due to that, and we'll take a look at that in a minute when we come out into this 0.86 micron region and actually be able to see that same scene and the changes on the ocean floor. Now, as I mentioned, this lecture is going to go about an hour, 15 minutes or so, so just be aware of that. This is the Earth-emitted spectra that's overlaid on various Planck function envelopes. Paul showed this yesterday. Here's the Planck function at 300. Here's the Planck function at 200, 260. So you can see that the temperature of the Earth that we were looking at in this case was probably right around 290. And you see that in a window region out at 0.86. Now, you may not have thought of that as a window region, but that's a very good window region. The only thing is you got some surface stuff that's going to play with you when you look at that window region. Large window region here with water vapor absorption becomes very important. Then a very nice window region down here in the 3.9 micron area, less water vapor absorption. So for ocean temperature, this channel at 0.86 and the channels at 10.7 are good combinations to use when you go out and begin to look at that, although you do have a lot of water vapor absorption showing up in here and maybe a few other gases at the 0.86. This is a big water vapor absorption region. This is the ozone absorption region at about 0.97. Then the strong carbon dioxide absorption between about 13 and 16 microns. So its water vapor absorption is very active on the left-hand side, from about 0.48 out to about 0.8. Ozone in the middle here is a very active absorber at about 0.95 to 0.9, or around 10, and then water vapor on the right-hand side. Also, this very sharp dip at about 4 microns is due to CO2 absorption, very strong CO2 absorption in that region. The problem with using that for soundings, of course, is during the daytime you're going to have reflection. But when the temperatures get warm out here in the lower parts of the atmosphere, you get a very rapid increase in brightness temperature versus what you see if you don't have the reflection from the sun. So a good nighttime sounding channel, not the best thing in the daytime. Let's take a look at this region that I've got in the circle, the 3.9 micron region. What can you do with imagery in this area? There are a multitude of things, especially when you use it in a multispectral fashion. And really, this channel should always be used multispectrally, never by itself, or rarely by itself. Nighttime fog, stratus, and cirrus, you can determine supercooled clouds, fog, ice, water clouds over snow. Winter storm has applications, land and sea surface temperature, urban heat islands, fire detection. It's been the hero in that for a number of years. Sun glint, I think Paul showed something yesterday. Sun glint from this is much wider, broader than it is for other channels, so it can tell you something about ocean surface roughness. Cumulus bands at night. Convective cloud phase, we can tell when we go from the water phase to the ice phase, and it's even good for volcanic ash monitoring. But again, this is when you use it in combination with other channels. This curve Paul showed yesterday, this is the width of that channel on GOES. It goes out to the current GOES system. It goes out to about 4 microns, but we don't go beyond that because of CO2 absorption. This is the reflected component from the sun. A lot of this gets absorbed as it comes into the atmosphere, but when you hit clouds, you get a lot of reflected component versus the emitted component during the daytime. And that's one of the things that makes it very useful for determining cloud phase, because water clouds are very, very reflective with smaller drops. Ice clouds have drops 5-7 times as large as the water cloud, and you'll get much less reflection. So let's take a look at signal and noise with this. We talked about it yesterday. Again, you're closer to linear at the top part of that Planck curve at the temperatures we deal with in the atmosphere on our Earth. Maybe not on Mars, maybe not on Venus, but here it's basically linear. So when we have a radiance error at 10.7 microns, really when you get into the cold cloud area, you haven't decreased your performance by that much, maybe a little over a half. You go to 3.9 microns, a temperature error of 0.23 degrees at 300 K is going to translate into an error out at 230 degrees K of plus or minus about 6 degrees. So you need to be very careful when you specify instruments that you have the performance in the region you want to. Pushing the 3.9 micron to give you very good performance at 230 degrees K may be a fool's errand, may be something you don't want to do. But you may want very good performance from about 273 to about 250 K where after you get much colder than that, you're pretty sure you're going to be into an total ice situation and maybe not a mixed phase. I've got two things on here. The left-hand graph shows single scattering albedo for water. That's the dark solid line, versus single scattering albedo for ice at minus 50 C, the dashed line. Those two curves aren't too far apart. And you usually multiple scatter 2-3 times, so you begin to multiply to get the amount of energy getting back to the satellite. The thing you got to realize is when you look at water droplet clouds, what size are they? What size are those cloud particles? They're all in the 10 to 15 micron range, or less, even for some fogs. They're really, really short wavelengths. When I start to look at ice clouds, I'm out in the 30 to 50 or even larger range. So my multiple scattering for ice, wow, I don't get much energy back at all. I do get some, but not near what I get back for a water cloud. So water clouds much, much more reflective at 3.9 microns than ice clouds. Furthermore, the water cloud is going to be warmer, so I've got more emission. The ice cloud is going to be colder. I have less emission coming from it. So everything working for me is low radiance coming from the ice cloud, high radiance from the water cloud when I'm at 3.9 microns. This is response of 3.9 and 10.7 microns to temperature variability within a single field of view. Now the Planck curve is not linear, and the response to variability within that single field of view allows you to look and see, if we have a fire at 500 degrees Kelvin, average over this field of view, 4x4 average, average fire temperature of that, and a surface temperature surrounding about 300 degrees K. So if a tenth of that area is covered with fire at 500, we're going to have a temperature difference of about 42 degrees Kelvin between 3.9 and 10.7, with 3.9 being hotter. As we fill up the field of view, of course, they're the same. If 50% of the field of view is filled with fire, we're up still above the 30 K. Now, most fires don't fill up a whole pixel, but sometimes if you have the big ones, they do. And they can be hotter than this as the fire temperature. But this increased response is why when you look at that 3.9 micron channel, it's much brighter where you have fires when you compare it to 10.7. If you don't compare it to 10.7, well, you can't do as good a job. The other thing I have here is spectral awareness with regard to surface characteristics. The blue line is water going across here. So this is emissivity of water. It's pretty high. If we look at the emissivity of trees or green substance, trees, grass, or whatever, that stays fairly high too. But there are a couple of regions where it's very clear that the surface emissivity is different, much different than one. One is over red clay, and one is dry sand. So when we have red clay and dry sand, and we're looking at them at 3.9 microns, they're going to be cooler at night. The emissivity is less, but we would turn that into reflectivity, and they may be brighter during the day. Similarly, when we go out to 8.6 microns, look at this. Dry sand has a hugely low emissivity, whereas the green area has a much higher, higher emissivity, and red clay and soils like that have a different emissivity. So surface characteristics can really cause the image to look different, and you need to be aware of that. So now, let's go in and do a little image analysis, being dangerously armed with what we just learned. So here on the left we have an image out over the coast of California where there's the letter V. We see bright areas and product It's the reflective component of 3.9. So we've taken out the 10.7 contribution. So here we're just looking at reflection at 3.9 microns. And it's very interesting. You see these lines very clearly. That's because they're ship trails and they have very small particles. If you look at the cloud field they're embedded in the visible, there's some places where it's just as bright as a ship trail, but you get over here at 3.9 and it's basically dark. And that's because those are marine stratocumulus type cloud, very large water droplets, poorly reflective. Okay? If you look up here in the upper left-hand portion of the picture, you see a bright white area moving inland. That's at point A where it's black at 3.9 microns. That's because it's a cirrus cloud, it's cold, and it's very poorly reflective. Okay? If we go over here to area C, we're bright at 3.9. We're bright over land, and that's a water cloud over land. Continental cloud, smaller particles versus similar clouds over water. We can see there's fog moving down the coast of California, very small particles, and it's and we see it in the visible as well as 3.9. We're going to look at area D, where we have differences in brightness. Those are differences, I think, in soil texture, soil types over the over parts of Mexico. If you look in the Arizona and New Mexico, you'll see some light-colored cloud moving over there. If you look at 3.9 microns, the reflectivity part, it's very streaky. Actually, those are small particles that are contrails from aircraft. And finally, the state, it's right above C. You see a bright area in that. That's a fire. Now, you don't see it at all at 10 point, or in the visible channel. Now what I'm going to do is, as you might guess, I can animate the one on the right-hand side, and we're going to animate it together with the other one. So you can see the fog moving down the coast. The ship trails show up very brightly. The dark cloud moving inland in the right-hand image is cirrus. If you look up near the Great Lakes, you'll see areas of darkness moving down across the white clouds. This is the state of Iowa, has that big black dot patch move across that. That would be cirrus cloud going over the top of some water cloud. That will be, maybe I'll point with a hand, that's right in this region. Same thing up here, cirrus cloud. This black area that we have through here, though, that's just open space over water. If you look in this area, the bright sparkling that's going on, that's characteristics of fires, and this is actually where farmers are burning off their fields. This area up in here, that just stays light white, it doesn't show up in this at all, is due to differences in land surface characteristics at 3.9 versus in the visible channel. So there's just a wealth of information that you can get here. The one thing you also ought to notice, right here, this very bright area in the visible image over California is snow on the mountains. Notice how you don't see it at all because snow is not reflective at 3.9 microns. This is one of the most valuable channels you can ever use. Here's just an example of a 10.7, a regular 3.9 micron channel in this reflectivity product. And what I've done is I've measured the temperature of the clouds at point A, point B, and point C, where I know they're water clouds, and lo and behold, these are out over the ocean, the cloud top temperature of 4C. Up here in area B, the temperature is between minus 12 and minus 15 degrees centigrade for a water cloud. So we know it's super cooled. You fly an airplane into that cloud, you're going to get icing. Fires, we've discussed that a little bit. We have an excellent fire product at Nestes, and we can pick out fires every half hour with our geostationary satellite data. And when we started this lecture, you remember I showed you the fires over the USA that are going on today, and I'll show you that again. Of course, we've been detecting fires over using ADHRR for years. These are over Borneo. It's in a El Nino year, so you're dry over in this region. And when you get a lot of fires like that, you get a lot of aerosols. End of the year, a lot of lowering in visibility, changes in Earth radiation budget, and so forth. MODIS is very good at detecting fires. You can see fires on a routine basis from MODIS, and you see Ndvi, and you can get those data from the virtual lab and look at them every day. In the virtual lab, when you go to the MODIS site and you click the area, it shows you the area you're going to be looking at, so you don't have any question as to where it is, and then you can go and look at the MODIS data. Let's look at this area out here in the water vapor absorption band. Again, I want to talk about that a little bit using this image here. This is an AIRS image over the U.S., and when we look at our water vapor channels, these are for sounding, but it's very similar for the channels that we use to look at moisture, the 6.7 micron channel. We use an area here where we go over a large region. There's a lot of variability in here. So what we're going to do is look at a movie across this region, and I want to just show you the variability you get where you have a normal water vapor channel. Okay? So when you think of water vapor and people ask you, well, is that at 200 millibars or 300 millibars or 400 millibars? You say, that question is really not applicable because it's representing the moisture that is throughout those layers as well as the temperature distribution. So let's take a look at this movie, and what I'm going to do is stop it. Whoops, I don't want to do that. I want to start it again. I want to make it go pause. And I'm going to grab the slider, and I'm going to come down here. Now, if you look up at the top of this thing, I'm going to stop it at 6.7 microns. Here's wavelength. Paul deals in wave number. I deal in wavelength. So here's the 6.7 micron channel, high in the atmosphere. Let's look on either side of it and see what the variability in that temperature field is that gets averaged together to give you that image. And lo and behold, it's considerable. It goes from about 210 to about 260 degrees over this short region. Now, most of it's very cold. So that gives us a pretty good idea that we're looking at cold temperatures, but we don't know exactly where. Back over here in the lower level water vapor channels, again, you can see online, offline, there's quite a bit of temperature variability. Now, I think it's somewhat a miracle that we can take a channel this broad and derive thermal sounding information from it in the first place. And this is one reason you have just got to go hyperspectral if you want to look at that. So if we look at the GOES 9 or the GOES 12, 6.7 micron channel area, we're seeing a region like that. Now when we look at our beautiful image like this, we see the drier regions and the more moist regions. We have to realize we're really looking at a movement through a layer in the atmosphere. Fortunately, as we get up high in the atmosphere, the motions are very well correlated. So we can actually see that very well in the motion. But we're looking at a motion of the broad layers of the atmosphere with this. Beautiful information, but we really need to know what it is. Let's just take a look out in this broad area, and I am not going to look at the ozone channel. Paul showed that yesterday. We use it for sea surface temperature by taking the moisture in the moisture in this region and helping clear out this channel by, well, statistically is the way we mainly do it, very little physical retrieval. But we try to figure out what the temperature is along here in a broad channel versus here in an absorbing channel, and we do ratios to get the surface temperature. And we can get very good ideas, especially of gradients, in the ocean surface temperature. This is a Coast Watch product. We can see things like the onset of El Nino very well by doing cloud clearing and then anomalies. So we can do El Nino, watching the rise in the water here over time. We can do very good thunderstorm cloud top identification of cold areas, warm areas. We can use the visible to see the plume, and then we can use the reflectivity at 1.6 and 3.9 microns of that ice cloud to tell where we have smaller particles above the anvil versus similar regions where we don't, and begin to say things about updraft strength. Okay, why aren't you going down? Well, I've got a computer freeze up here. Hold me just a second. Go to the task manager. Okay, keep running. Now it goes to the next one. In a similar manner, and I won't go over this in detail, but you can look at the brightness temperature versus the spectral band, and certain things like water cloud, snow, ice cloud cluster differently in the different bands. And by using the different bands together, like I showed you visually, you can actually go in and do cloud type identification and cloud composition. This is a 4-panel image: visible, infrared, thermal infrared, 6.7 micron infrared, and this is a reflectivity. It's over a large part of the United States, and I'm going to make it go in a movie. You can see that this is over Lake Michigan here. You can see the band of water cloud over the lake very clearly. And I'm going to point with the hand again because this is being recorded. So here's Lake Michigan. Here's the water cloud. We can tell it's water cloud by looking at its reflection here. This whole area out in here is snow. You can tell it's snow. It's not reflective. This region that is bright in the 3.9 micron reflection is going to be water cloud out in that area. You can see it in 10.7. You don't see it at 6.7 because it's low. The black region here is cirrus, and you can see it's showing up in the water vapor channel very nicely. By taking the 10.7 micron temperature for much of this, you can tell if that cloud is supercooled or not. So again, a wealth of information in there. I want to look at surface characteristics out in this 8.6 micron region. This is that same movie, and they'll both start going in a second. I think what I'm going to do is, in the visible one, vis to near IR one, if we can get it to repeat, we'll just stop it right there. Now you see there are differences in, well, I thought I stopped it. Stop. Stop. Well, my computer's being like a naughty child and not obeying. But again, you see differences in the land surface characteristics here. And those differences in land surface characteristics, when you look at the vis to near IR movie, you can actually correlate those to what we see in the vis to near IR. And I'm going to stop this one, maybe let this one go for a second. Now I'll stop that one and let this one go. There, this is better. So you see the green area, it has very different characteristic out here than it does in this more sandy area. Some of these hills in here appear not too differently in the vis to near IR portion of the spectrum. So you can actually take the different channels and do things about land surface characteristics as well as follow the dust at night. Today's satellites, we have many channels from which we can obtain information. We've already gone over the brightness characteristics to the visible. We can enhance the infrared channels to look at special things. And I showed you at the very beginning, you can use them either separately or in combination to retrieve a wealth of information. But what I see happening is we're going to be moving into satellites that have 15 channels, 12 channels, all providing information And the data is going to be coming down every 5 to 15 minutes. So how do you put that together usefully for somebody to use? It has to be through product selection. And one of the things I see is doing multi-channel products that are based on principal component analysis, where you take the principal components which show you different amounts of information in the imagery, you put those together, discuss and do research and find out how you can really present a single product from multiple channels to give you information on ground, clouds, moisture, and so forth in the atmosphere. I really don't see any other way to contend with that. I want to look very quickly out in this long-wave CO2 absorption region. Paul covered it fairly nicely, so I won't spend much time out here at all. Just to point out what now I think should be obvious to just about everyone. Before, these numbers 1 through 15 here, or 1 through 18 are the channels that we normally use to sound the atmosphere, and you can see they're fairly broad channels. If you look within those channels in the various absorption regions, the variability is incredible. So the idea that we could do soundings, that's why the soundings aren't super good. They are super good for the information they contain, but that information is a conglomeration of many of the various lines. And that's why you want to go to the hyperspectral area to do your sounding. One of the interesting things, though, is as we get out into the absorption regions and we begin to look at them, and Paul, I believe, showed something like this yesterday, we have in the 10.7 micron region, out to 12 microns, we actually have fairly strong water vapor absorption, but we also see down to the surface where there is no water vapor absorption. So by looking at the temperature of the water vapor above the surface, we can actually tell if we have a inversion or no inversion. And the important thing about this is a couple of things with the geostationary satellite. We'll actually be able to sit, and by looking at spectra like this over time, we'll be able to see this line right here go up related to surface temperature. We'll be able to tell when convective mixing is starting, watching these lines change over time, because they'll go down as it becomes more adiabatic lapse rates through the mixing. So you'll be able to tell actually how fast you're approaching convective onset. Similarly, at night, we'll be able to watch the moisture above the surface. It probably won't change its temperature very much, but this line will drop down, showing a stronger and stronger inversion. And what a stronger inversion means, in most cases, is, number one, if there's pollution in there, it's not going anywhere because you've got an inversion that's trapped it. But number two, if you're in a summertime situation that you might form a low-level jet, you've just decoupled surface friction. So you can have moisture stream rapidly to the north in our hemisphere anyway, in that low-level jet, and cause convection 100, 200 miles away from where it began hours ago, because it doesn't have to go through the mixing process to get where you want to be. Now, I'll cover this again a little more on next Tuesday when I talk about convection. Things like this are very, very exciting. The microwave portion of the spectrum, it looks complicated in a way. We don't deal with it that much. The microwave portion of the spectrum, the linear relationship with brightness temperature just makes things a lot easier in some ways. However, some of the emission and reflection changes the way we look at things, and where you are is very important. But we have tutorials on this. There are various uses. If we look at land and ocean surface properties, for example, some of the things that we can infer are land surface temperature, wetness, vegetation, ocean surface wind speed, not velocity. Well, some people say you can from polarimetric considerations and so forth that we're trying to do with INPOs, but they're finding in low wind speed regimes you don't get very much information. But with SSMI we can get velocity. That's what's shown here. And these are the basic channels that are used to get that, to derive these products. And the microwave process is, for land and water, is emissivity, contrast, variable land emissivity for soil moisture, rough or smooth surface for ocean wind speed, and ice versus sea ice covering, and scattering by snow and ice. One of the things that we know we do with microwave very well, because of our ability to see the ice clouds very clearly at the 85 gigahertz channel through absorption and emission, and we can tell large droplets, small droplets, water content, is go in and derive rainfall. Now this is a hurricane here, and that hurricane was very poorly forecast, and instead of recurving like everyone thought it would, it came to this point and stopped and just continued to move around. And over that time, very heavy rains occurred in this region. Now the hurricane stopped up here, and it stayed up there, but the heavy rains were down here. And the main reason was the low-level cyclonic flow brought in Pacific moisture that ran up against the mountains and caused a lot of rain in that area. But from the microwave, we were able to actually measure the rainfall over time and show the devastating rainfall that occurred in that area. And in fact, geostationary microwave, because of the footprint size, I believe it's done, its main application really will be to look at rainfall over time frames shorter than what you want to look at with a polar orbiting system. This is one of the most beautiful products that comes out of our microwave systems. This one on the bottom right is total precipitable water over the ocean. Again, the key parameters that you look at are in the middle box, and the potential uses are in the right. But this precipitable water that you get from the AMSU and SSMI 22 gigahertz channels allows us to actually see the coupling between mid-latitudes and tropical regions. Also the high amounts of moisture down in the tropics, and you can put them together and make a movie. Now we do have problems with land emissivity and coastlines, and you'll see some coastline movement a little bit, and you'll see the land has nothing over it because we're still trying to work the problem. Down here on the bottom is total precipitable water in millimeters, going out to the brightest purple of 75 millimeters, and in the green area it's like 25 or so millimeters of water. 0 to 12 in the blue. So over the oceans, a lot of areas you don't have a lot of mixing, a lot of water vapor above the ocean. But look at the ITCZ, the very heavy concentration of moisture there. Also notice how you can see things like these waves moving along, interacting with the westerlies, and the westerly trough actually pulls that moisture up to the north. Where you have the very high concentrations of water vapor in the blues and purples, we actually see those correlating very well with the tropical cyclones. But again, the mid-latitude and tropical interactions are very, very clear. It's also clear to me the northern hemisphere and the southern hemisphere weather are very similar, but in ways very different. Notice how well you can see the fronts and convergence zones in the southern hemisphere, where in the northern hemisphere with so much land, we don't see as much of the ocean region and some of these interactions and breakdown of the frontal zones. You can take the principles that Roger Weldon taught about mid and high level water vapor and look at this water vapor field and do the similar things with deformation zones and so forth. This product is one you just got to have people use. You can see the buildup of moisture, deep moisture in the Indian Ocean area, and what people haven't done that somebody's got to do is take a look at the Madden-Julian oscillation and this buildup of heavy PW, and then the wave move across from west to east like it does. So there's a wealth of information to be gleaned from this system. And when we have more satellites providing information in this region from polar orbit, we'll actually be able to get more continuous loops and do a much better job of forecasting this. And you can just see coming up into parts of China how you can see the increases in this moisture that will come up here in certain times of year and go with some of your heavy rains. Now in the U.S. we actually have GPS total precipitable water products that we blend with this over land, so we're actually able to carry this animation over land areas. Active sensors are providing a lot of information. We covered some of that yesterday: altimetry, wind speed, ice field characteristics. This is altimetry. We like to show this one over the U.S. We see the loop current where we have deep warm water over the Gulf of Mexico that's important for hurricane intensity. Down here on the lower left, we actually see the increase in sea surface height that's going with the development of an El Nino, which you may not think is important over here, but you got to realize with El Nino, you get a lot of subsidence over in this region over here, so you get a change in your weather system. Global winds from the QuickScat system are providing a lot of information about the flow over oceans, which goes with your Bowen ratio, your sensible and latent heat flux off of the oceans, moisture transport into the atmosphere, the ITCZ. I mean, you can put all of this information together in composite products and really milk the meteorological information. Synthetic aperture radar gives wind speed products that are very nice. And I showed yesterday how you can actually use synthetic aperture radar, multiple passes over polar regions to track icebergs and actually look at variability in the ice shelves, which is darn interesting. Rainfall missions, active radar, actually looking at the precipitating clouds as they pass over with their own passive microwave instrument, and then underflying polar satellites providing intercalibration for a global precipitation mission. The importance of trains of satellites, formations I talked about yesterday, being able to blend research and operational satellites into a single system and get the best information from both, plus replacement policy and things as satellites become much bigger, reducing risk of launch failure, of loss of total missions, I think clearly points to going toward formation flight instead of single large satellites about as big as this room with multiple instruments on them. Every time you add an instrument to a satellite, you increase its chance of failure. Because that instrument fails, it can cause you to have to launch that whole satellite again. And wow, that is very, very expensive. Whereas if you have a modular system, you're not faced with that problem. You're faced with the launch cost problem and the operation problem. But still, you may have a more robust system. Active LiDAR will begin in space. The European and French will first do this with the atmospheric dynamic mission, and we'll actually be able to look at molecular layers. So we'll actually have aerosol concentrations in various layers, but we'll be able to see their movement and along one axis and infer wind speed. GPS radio occultation. I talked about this yesterday, but these are figures of a observing system simulation experiment. It's in the Quarterly Journal of the Royal Meteorological Society. You can see that on the bottom if you wish to get more detail. But it talks about how greatly you can increase the accuracy of soundings in the vertical by combining GPS with hyperspectral data. That's the end of the spectral bands presentation from my part. I just want to say we're in a golden age of remote sensing for a variety of meteorological applications and land applications. The synergy between components of the space-based portion of the global observing system is the way to the future. Synergy, synergy, synergy. And understanding the capabilities of the observing system you work with is exceptionally important as you try to move forward into the future. Thank you. And again, for those that missed it, this is from this morning. In this area with all these bright spots up through here, all the way up into here, those are fires. And we're able to watch them every 15 minutes with our GOES system. I think that's incredible. And now, since you've all become experts, you can see the marine stratus here. The black areas in here are obviously cirrus and thunderstorms. A lot of information. Lots and lots of information. Okay? So that was an hour, a little under an hour and 15 minutes. Thank you.